So in this lesson of HEC chemistry, we're going to be exploring atomic absorption spectroscopy, also known as AAS. So before we even jump into AAS, let's have a look at the relevant inquiry question and dot point. So this relates to applying chemical ideas module 8. So we're on the first inquiry question, which is analyzing ions. Now, AAS is under this particular dot point, and the key thing you need to know is there are two things you must know about AAS going into your exams. The first most important thing is you must be able to explain the methodology of AAS. An even more important point is you should be ready to perform calculation questions using AAS to determine the concentration of metal ions in a solution. Before we even jump into AAS, let's have a look at what the word spectroscopy refers to. So spectroscopy is a study of how matter interacts with energy. So we're going to input some kind of energy to matter and observe how it responds to it to determine its concentration or its bonds, etc. Now with AAS, the energy that you input is electromagnetic radiation. This refers to all the waves that travel at the speed of light, so that's approximately 3 times 10 to the power of 8 meters per second. We categorize these waves based on their frequency/wavelength. Now here we have high energy waves, and here we have low energy waves. High energy waves have characteristically high frequencies. So you can see that here with waves oscillating up and down numerous times per second. Contrast that with a low energy wave, which has a very low frequency. So there's a low number of oscillations of that wave. You can also see that the distance between two peaks of a wave here are very, very short. That is also characteristic of high energy waves. They have a high frequency and a low wavelength. Correspondingly, the distance between two peaks of a low energy wave is very high. So low energy waves have a longer wavelength and a lower frequency. The relationship between frequency and wavelength is summarized in this equation here, where c is the speed of light, it's constant, and hence when f or frequency increases, the wavelength, which is lambda here, will decrease. Now that we understand the energy that we're inputting to matter in AAS, let's study how matter interacts with that energy. The key point is that all elements are picky with the energy they absorb. So when you expose an element to the entire electromagnetic spectrum, everything from gamma to radio waves, it is extremely picky and only absorbs a few particular wavelengths of EMR. The second principle is that the degree of absorbance of these wavelengths is directly proportional to concentration. So what that means is as absorbance of these characteristic wavelengths increases in a solution, for example, we can say that there must be a greater concentration of that particular element in the solution. Now, it's summarized in the equation A equals to Kc, where K is a constant, and hence when A increases, C also increases. This is a modified form of the Beer-Lambert equation, which is used with colorimetry, UV-Vis spectrophotometry, and AAS. So here's a final equation to highlight the relationship between absorbance and concentration. So if a sample is concentrated, there's going to be a lower intensity of light when the sample is present because it's going to absorb it. And hence when the denominator increases with a greater concentration, this overall value here, this fraction, will increase, and hence absorbance increases with increasing concentration. Key take-home message, as A goes up, C also goes up. Let's study what actually happens when we say an element absorbs electromagnetic radiation. So it's specifically the electrons of that atom which will absorb the incoming electromagnetic radiation. So here we're looking at a model of the nitrogen atom. So when we input electromagnetic radiation, the nitrogen atom will remain stable until a particular wavelength of EMR comes in. The nitrogen will then decide to absorb this EMR. And when the electron absorbs this EMR, it jumps to a higher energy level, as you can see here. Now, the energy that was gained by the electron is directly proportional to the frequency of this light here. Now, what you'll also notice is that eventually the electron will have to de-excite back down to a lower energy level. This is known as ground state. And when an electron de-excites to ground state, it's going to re-emit that exact same electromagnetic wave. And that is simply due to the law of conservation of energy. When the electron gains energy, The energy must have come from somewhere, which in this case was the wave. And when the electron returns back down to a lower energy state, the energy difference is released as EMR again. The implication of this for chemistry is that the absorption spectra of an element is exactly complementary to its emission spectra, as you can see here. The same wave that was absorbed is re-emitted by a particular element. We've already highlighted that as absorbance increases, we can say the concentration of that metal cation in solution will also increase. Here's a very clear example which shows you the complementary nature of an element's emission and absorption spectra. Now I want you to imagine this. Imagine you have a container, a tube, a glass tube with hydrogen gas inside it. Now if you apply electricity to this tube containing hydrogen, its electrons will excite to a higher energy level. And when they de-excite, they're going to release specific wavelengths of EMR. Now here you can see the overall EMR spectrum. Now you notice that hydrogen isn't releasing every single wavelength of EMR. It's very picky. It's only releasing one wave here, one wavelength here, one wavelength here, and here. This is hydrogen's emission spectrum. Now take another thought experiment. Imagine you have that same tube containing hydrogen gas. Now instead of exciting it with electricity, you pass white light through the tube. Now note, white light contains every single wavelength of the visible component of the electromagnetic spectrum. Now again, see that the hydrogen isn't absorbing every single wavelength. It's very picky. It's only absorbing one wavelength here, 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 and here. Now what do you notice? The wavelengths absorbed by the hydrogen, aka its absorption spectra, are complementary to its emission spectra. AAS studies metals. So it's not hydrogen, so we're going to go through a specific case example with sodium. So you should clearly know which one is the emission and absorption spectra straight away. This black strip with two wavelengths emitted is sodium's emission spectrum. Correspondingly, the two exact same wavelengths that were absorbed are sodium's absorption spectrum. So you can see clearly the absorption and emission spectra are complementary, and this also applies for metals. So now we're ready to go through the methodology of AAS. And the overview is we are trying to determine the absorbance and hence concentration of a metal cation. So what we do is we have a beaker containing a metal cation. We try to bring the solution into this flame. And what the flame does is it atomizes the sample, meaning metal cations exist independently over this furnace. Now the metal cations are over the furnace and they're exposed to electromagnetic radiation. Now the metal cations are going to absorb specific wavelengths that correspond to their absorption spectra. So if 100% of EMR was released here from this cathode lamp, less than 100% will pass out of the furnace because a small percentage was absorbed by the metal cations. So what we aim to do is we aim to measure the absorbance value here and hence determine the concentration of metal cations in a solution. So let's run through the details here. So you have a beaker, you have a solution containing the metal cations. Now, AAS is known for measuring the concentration of metal cations in very, very trace amounts. So even if you have 1 part per million or 1 part per billion of a metal cation in the solution, AAS will be able to determine its absorbance and hence concentration. So it's a very, very accurate quantitative ion analysis technique. Going back to this example, let's say we're studying mercury, because that happens to be a trace heavy metal that we don't want in the environment, and hence we're going to monitor. Now, mercury gets brought up, aka aspirated, into this chamber here. So we have a mist of solution containing your mercury atoms. Now that's combined with a fuel, let's say a hydrocarbon such as octane. And the fuel is present with its oxidant. So in this case, it's oxygen. The fuel and the oxidant are super important because they allow combustion when this entire sample reaches this furnace. So this entire mixture is brought up into the furnace, and the furnace provides the energy for combustion. Now, combustion at the furnace atomizes the sample. That is a key buzzword you must mention in your HSC responses. The furnace atomizes the sample, meaning individual mercury atoms now remain over the furnace. So they're just floating on top like this. Now, at the same time, we use a specific lamp for mercury. Since we're studying mercury, we're going to use a mercury cathode lamp. And the cathode lamp consists of a piece of mercury connected to an energy source. So when we provide energy, usually in the form of electricity, the electrons of the mercury will excite to a high energy level. Now, when they de-excite, they're going to release the specific emission spectra of mercury. So here we have specific wavelengths of light that only mercury emits and absorbs. So these specific wavelengths of light, the emission spectra, then pass through the furnace. And guess what's the furnace? We have our mercury atoms. They're going to absorb all these specific wavelengths to some degree. So I'm just giving you an example here. If 100% intensity of light passed through and 30% was absorbed, that means the intensity of light coming out of the furnace is only 70%. And hence we use that to determine absorbance and hence concentration. So in this furnace, the mercury atoms are going to absorb all the wavelengths to some degree, and that's corresponding to the absorption spectrum of mercury. The only reason that these mercury atoms absorb the wavelengths here is because the emission spectra released by the mercury metal here is complementary to the absorption spectra of the mercury atoms over the furnace. Now we have the light then moving through here through a monochromator. The sole goal of a monochromator is to study one specific wavelength. We know all the wavelengths were absorbed, about 30%. So studying all the wavelengths will not give us any additional information, and so we only study one wavelength. And this one wavelength is passed through a photomultiplier to amplify the signal, and then computer technology to determine absorbance. And from absorbance, we'll use a calibration curve to determine concentration. Stay tuned to understand how to interpret calibration curves in AAS.